In Module 4, we're going to start talking about triangles. And to start us off, we're going to talk about how we classify triangles. And we have to first talk about the different parts of a triangle. So remember, a triangle is a three-sided polygon, which is just another word for shape. So it's a shape that has three sides. And the way that we name a triangle is from the labels of the vertices. So it's named from the labels of the vertices. And you can start with any vertex when you do this. So if we're looking at the triangle we have to the right here, there are quite a few different ways we can name this triangle, but I'm just going to list two. So one of them would be triangle WXY, and we do use the little triangle symbol to let us know we are talking about a triangle. Another way we could do it is triangle XYW. And as I said, these are not the only two ways to name the triangle, they're just a couple. Next, we have the sides of a triangle, which are the segments that make the triangle. And since a triangle has three sides, there are three segments that make the triangle. In this case, that's going to be XW, XY, and YW. Next, we have the vertices, which are the corners of a triangle. And our vertices in this case are W, X, and Y. And lastly, the angles. And angles are formed where two sides meet. And if there are three vertices, there are three angles as well. And I'm going to name the angles by their vertices since there aren't multiple angles. So we have angle W, angle X, and angle Y. You could also use three letters to name each of these angles, but that is unnecessary since there's only one angle at each vertex. So let's talk about how we classify triangles by their angles. So there's four different ways to name a triangle based on their angles. And the first is an acute triangle. In an acute triangle, all three angles are less than 90 degrees. So all three angles are less than 90 degrees. In an obtuse triangle, one angle is greater than 90 degrees. And the reason why it's only one angle is because triangles have three angles. If there's more than one angle that's greater than 90 degrees, you get more than 180 when you add the three angles together. And since we've already figured out that the sum of the angles in our triangle is only 180 degrees. Next, we have a right triangle where one angle measures 90 degrees. Similarly to obtuse, it's only one angle because if we have multiple angles measuring 90 degrees, we get more than 180 degrees, which can't happen. And lastly, we have an equiangular triangle, which is when all three angles have the same measure. We can also classify triangles by their sides. And there's only three different ways to classify a triangle by their sides. The first is a scalene triangle. A scalene triangle has no side lengths equal. So all three side lengths of your triangle are different lengths. Next, we have an isosceles triangle, which is when at least two side lengths are equal. And lastly, an equilateral triangle, which is when all three side lengths are equal. And you can classify a triangle by both its angles and sides at the same time. So you can have an acute scalene triangle or an acute isosceles triangle. You can combine angles and side when classifying. So we look at this first example, we want to identify the indicated type of triangle. So in A, I want to identify all isosceles triangles. So isosceles have two or more sides the same. And if I look, I know that side AB and side AD are the same since they are congruent. And I also know sides BE and DE are the same because they are congruent. So now I just need to figure out triangles that contain those two sides. So triangle ABD would be isosceles. It would contain sides AB and AD. And then we have triangle BED. It would also be isosceles. Next, we want scalene triangles. So scalene triangles have no side lengths the same. So I have to come up with triangles. I can't have a triangle that has both sides AB and AD in it, or BE and ED. But I can have one of them. Since I don't know that AB and EB are congruent to each other, I can have a triangle that contains those two sides. And I can also have a triangle that contains sides AD and ED, since they are not necessarily congruent to one another. So that would be triangle ABE and triangle ADE. Those are also scalene. We can also deal with smaller triangles inside our shape as well. So we don't know anything of the lengths of BC and CD or AC and CE, so we don't know that any of those are congruent. So we can also say that triangle BCE is scalene. We can say triangle CDE is scalene. We can say triangle ABC is scalene and triangle ACD, based solely on what we currently know of this image. So more often than not, a lot of triangles are scalene than they are any other type of triangle. So in our second example, we want to find x and the measure of each side of our equilateral triangle RST. So equilateral means all three sides are the same length. I'm going to use that to find x first. So I just have to pick two of the sides to find for x, and I'm going to pick the two that I'm going to pick RS and RT, since 2x equals x plus 9 is going to be an easier equation to solve for x. So we subtract x from both sides, and we get that x equals 9. And because all three sides are the same, it doesn't matter which length I plug x in for to solve for the sides, since they'll all be the same. So let's just go ahead and plug it in for ST. So then we know that RS equals RT, which is going to equal ST, which equals 3 times 9 minus 9. 3 times 9 is 27 minus 9, and 27 minus 9 is 18. And if I were to plug in 9 for side RT, 2 times 9 is 18. And if I plug it in for SR, 9 plus 9 is also 18. So plugging it in for any side gives us 18 for all three side lengths. So in our third example, we want to find x, the length and the lengths of our sides JM, MN, and JN if our triangle JMN is an isosceles triangle. with the congruent sides being JM and MN. So JM and MN are congruent, which is what is going to help us solve for x, since we know those two have to be the same length. So we'll use the fact that 2x minus 5 is going to equal 3x minus 9. So I'm going to add 9 to both sides. So we get that 2x plus 4 equals 3x. And we're going to subtract 2x from both sides, and we get that x equals 4. So there's the first part of our problem. Now let's start solving for our sides. Well, since JM and MN are the congruent sides, let's solve for those first. So we know that JM equals MN, and let's go ahead and plug in x for the 2x minus 5. So 2 times 4 minus 5, which is going to give us 8 minus 5. So we get that JM and MN both have a length of 3. Then that just leaves us with JN to solve for. So JN equals x minus 2, so it's going to equal 4 minus 2, meaning that JN has a length of 2. And we have solved for all 3 sides of our isosceles triangle. So in our last example, we have that KL is a segment representing one side of isosceles right triangle, KLM, with K at coordinates 2, 6 and L with coordinates 4, 2. Angle KLM is a right angle and KL is congruent to LM. We want to describe how to find the coordinates of vertex M and name these coordinates. So the first thing I'm going to do is draw an X and Y axes on this grid. We have X and Y. I'm going to start with labeling my point K. So we need 2 along the x-axis, and then we need to go 6 on the y to get our point K. And for our point L, we need to go 4 along the x-axis, and then 2 on the y to get point L. And we know this is one of the segments on our triangle, which means we can connect these 2 points to get one of our sides. The next thing we know is that angle KLM is a right angle, which means our segments KL and LM are going to be perpendicular. So if we find the slope of our line KL, we can use that to find the slope of our line LM. That will help us get to our point. So remember, slope is found by doing y2 minus y1 over x2 minus x1. If we use L as our second point, we'll do 2 minus 6 over 4 minus 2, which gives us negative 4 over 2, which is negative 2. So remember, perpendicular lines have opposite reciprocal slopes. So that tells us that the slope of LM is 1/2. And we're going to use that in a little bit. Now we also know that KL and LM are congruent, which means their line segments are the same length. It also means the distance from K to L and L to M is the same. So now I'm going to use the distance formula. So the distance formula, remember, is x2 minus x1 squared plus y2 minus y1 squared, all underneath the square root. Still using L as our second point, that's going to give us the square root of 4 minus 2 squared plus 2 minus 6 squared, which is going to give us the square root of 2 squared plus negative 4 squared, which gives us the square root of 4 plus 16, which gives us a distance of the square root of 20. So I know the distance of LM must also be the square root of 20, and I can use this to set up what the distance formula should look like even though I don't have my point M. So we already know the distance is the square root of 20, has to equal underneath the square root. If we use L as our second point still, X is going to be 4. Then we're going to have minus X, and I'm going to put a subscript of M since it's whatever the X coordinate of my point M is, squared, plus my Y coordinate 2 minus YM squared. And eventually we're going to use this to help solve for one of our coordinates. So I'm going to come back to this equation a little bit, and now I'm going to use the fact that the slope of my segment LM is 1/2 to write an equation in point slope form. Since I know my endpoint M has to be on the line that contains point L, I can write an equation in point slope form. So remember, point slope form is y minus y1 equals m and then in parentheses x minus x1, where m is the slope of your line and then x1, y1 is the point on that line. So we know that the point 4, 2 is on our line, and we know the slope is 1/2. So when I plug that in, we get y minus 2 equals 1/2, and then in parentheses x minus 4. Now typically we would just leave this equation as it is, but we're actually going to simplify it for this problem. So I'm going to distribute that 1/2 into the parentheses. So we get y minus 2 equals 1/2 x minus 2. And then I'm going to add 2 to both sides, and we get that y equals 1/2 x. And I'm going to use this to substitute into that distance formula that I have. Since I know the y coordinate is going to be 1/2 of the x coordinate, I can use that in my equation. So I'm going to take the square root of 20 equal, and then underneath the square root we have 4 minus, and I'm going to go ahead and just leave it as x now, squared plus 2 minus, and then instead of writing y, I'm going to put 1/2 x squared. So now I have a distance equation that only has the variable x, which is a lot more useful in solving for one of the values of our point. So first thing I want to do in solving for x is to get rid of the square roots. So I'm going to square both sides of my equation. So when I square a square root, they cancel. So my left side is going to become 20 equals, and then the right side, no longer square root, is going to be 4 minus x squared plus 2 minus 1/2 x squared. Now I want to figure out what happens when I do 4 minus x squared and 2 minus 1/2 x squared. When I square something, it means to multiply it by itself. It doesn't mean I take what's inside the parentheses and square it. So this should be 4 minus x times 4 minus x, and the 2 minus 1/2 x squared is 2 minus 1/2 x times 2 minus 1/2 x. Now I can distribute into both sets of parentheses. So we're going to end up with 20 equals, and then 4 times 4 is 16. 4 times negative x is negative 4x. Negative x times 4 is negative 4x. Negative x times negative x is a positive x squared. Then we have plus, and we're going to do the same thing with our second set of parentheses. 2 times 2 is going to give us 4. 2 times a negative 1/2 x is going to give us negative x. Negative 1/2 x times 2 is negative x. And then negative 1/2 x times a negative 1/2 x is going to give us positive 1/4 x squared. And I know this is a lot of work so far, and some of you may feel a little overwhelmed, but this is a critical thinking problem, which means it's meant to push you a little bit further, go that little extra distance. It's not going to be a typical problem I'm going to expect you to be able to complete, but it's still a good way to see how we can use what we've previously learned with triangles and graphing. So let's go ahead and combine like terms on the right side. So we have 20 equals. We have 16 plus 4, which is going to give us 20. We have a negative 4x, a negative 4x, negative x, and negative x, which all combine to give us negative 10x, and then we have x squared plus a 1/4 x squared, and leaving that as a fraction, we get 5/4 x squared. So because my goal is to solve for x, that means I want all my variables on one side and the numbers on the other. So that means subtracting 20 from both sides. And when I do that, I get 0 equals, and I'm going to go ahead and reorder my right side and put the 5/4 x squared first, and then the minus 10x. So now we have the x's on one side, and now we just have to figure out how to solve for x. And those of you that may have factored before may notice that both of my terms on my right side have an x in common, which means I can factor that out. And when I do, I get x on the outside, and then in parentheses, I have 5/4 x minus 10. And this is how we're going to get possible x values for where my point M is. So I'm going to take anything that contains x and set it equal to 0. So my first possibility is that x equals 0, in which case the y-coordinate of my point M, if we go back to the equation of our line here, is found by doing 1/2 times x. So 1/2 times 0, which gives us a y-coordinate of 0. So one placement of point M is that it is at the point 0, 0. It's not the only possibility though, because we still have this 5/4 x minus 10. That could also equal 0. So when I solve for x, my first step is going to be to add 10. So we get 5/4 x equals 10. Then to solve for x, our first step is to multiply both sides by 4. We get 5x equals 40. Then when we divide by 5, we get x equals 8. So the second possibility for my point M is that it has an x-coordinate of 8. And then again, using the equation of my line, we know the y-coordinate is 1/2 of 8, which means my y-coordinate is at 4. So my point M could also be at the coordinate 8, 4. Both of these are possibilities for my coordinate. It's not like one or the other is the correct answer. Either one of them could work and still meet the requirements of my problem. So if we go back up and graph these two possibilities, so the first possibility for the location of my point M is 0, 0, which is the origin. So point M could be at 0, 0. The other possibility is that it is at 8, 4. So if I 5, 6, 7, 8, and then I go up to 4, I'm going to have point M. And both of these are going to make a right triangle where angle KLM is a right angle, and the distance from L to M is the square root of 20. So one possibility through the origin, that's one of the triangles, and then I can also have the triangle through the point 8, 4. Both of these have an isosceles right triangle where KL and LM are congruent, and vertex M with KL congruent to LM. So like I said, this is a lot more of a difficult problem, so please, if watching this you want me to go through it with you one-on-one, come up to me if you had a specific question about any point of this step, asking where did this come from, please let me know. As I already said, not something I expect you to do all the time. This is a very difficult problem, I understand that, but it's still important to see where things we've previously learned help us in constructing specific triangles based on side lengths and their angle measures. Also, as you're completing the assignment over this section, if you have any questions, please feel free to ask me.